Hello, it's Paul, and welcome to a new thing I'd like to do here on YouTube, where I revisit my youth and have a look at the old computers and what I did with them and why they were fun and what got me into this computing thing in the first place. So way back, before time, well, not before time, again, I presume it would have been very early 80s. I first got my hands on a Commodore PET in the school I was at. So these were first sold in October 1978, a 6502 processor, a tape deck for loading programs, and they had an astounding amount of RAM. The first ones had 4K, and then later on they had 32 whole kilobytes of RAM to be used. So they looked like this. Well, the ones we had didn't quite look like that. They had a separate cassette deck, and the keyboards were a little different. They were proper keyboards, not that horrible calculator thing. But anyway, that's roughly what they looked like. And they came with BASIC, and we can see the BASIC here. This is an emulator of a PET. I don't currently have a PET. I kind of wish I did, but they're big and they die and they need love and care, and but I do know people who still have PETs. But anyway, that's beside the point. So you can do things like write programs. So to write a program, now I'm going to do this a lot. Watch this, I'm typing in rubbish. I need to use the numeric keypad, and I keep forgetting to do so. So 10, print, inverted commas, hello Paul, and then run. And it prints hello Paul. I can type list. To see my program, I can add a new line to a program. There you go. That's my 20, go to 10. I can run that, and it'll keep printing hello Paul until I press the run stop. So basically it had BASIC, and you could, it's an interpreted language, obviously. It's an awful language, obviously. It's long, well, I presume there might be some people, but I mean, its place as an interpreted language has been killed by things like JavaScript and other interpreted bytecode machines, Java, that type of thing. And, but it did, it did its thing. It had strings, it had integers, it had floating point maths, it had ifs and fors and go-tos and go-subs, but it was horrible. And when we got our hands on it, we had a disk drive in our school, which was, I believe it was one of these 8050s, and we could do things like this. So we could do load, it was $, comma 8, and that in theory loads the directory, and then I can list it like a program, and it shows me the files that were on the disk. So this is what we spent our time doing. There were computer magazines at the time, and they used to things like PCW, Personal Computer World, and possibly Compute Magazine, and maybe even very early copies of Byte and various other things. And they used to come with listings of programs. So like half the magazine would be printouts of other people's programs, and you could type them in and you could save them, and they would be full of bugs, and you'd make silly mistakes because you had no idea what you were typing in. But anyway, and various games were had, like this one. Load BAT. So what is BAT? BAT is very typical of the high fidelity Call of Duty or Battlefield 1 like games that were available at the time. Hopefully this won't be too noisy. No, I don't want sound either. So that little flappy thing is me, and I've got to eat things. Yes. I don't think we'll be doing a full Let's Play for this game anytime soon. But as much fun as playing the games were, I really liked looking at them, trying to figure them out. And this is what BASIC looked like. So basically you would type that in, you would play it again, you'd realise that this game wasn't the best game ever, and it wasn't exactly what you had been looking for. So the next one would come along, but it was about learning. and playing the games. So eventually, you know, one of the, like, you know, after playing a few games, what you want to do is start writing your own things. So, you know, once you've done a prompt and asked it to type in your name and said hello, your name, we look at the screen, because I mean the screen is pretty much where everything needs to happen to get things out to the user. So let me just do this. When CHR dollar, it's 147, hopefully. Yeah, clears the screen. Right. So basically, on a Commodore PET, the screen was 40 columns by 25 rows, and each character here was 1 byte. So there were like 256 different things which could be displayed on the screen. If you include, so there's a blank, obviously was a blank space, so 255 actual characters, plus you could leave a space there which would be nothing. And the screen memory just sits in the main computer memory. So this, if you think about it, the 6502 was an 8-bit computer, i.e. every data instruction, everything it did could only do it 8 bits wide. It dealt with a byte at a time. But it could address up to 16 bytes. So it could address a full 64K of memory on the address bus, but the data bus was only 8 bits wide. So here we go, halfway in memory. What we see here is we see where the screen is. And that number 8000 in hexadecimal, or 32768 in decimal, is the location of the screen. And obviously 40 by 25, that gives us 1000 bytes, or 03E8 in hex. And by looking at games and reading bits and pieces about the Commodore, you could figure out that you could directly access, as well as doing a print statement, so like print inverted, which is how you'd normally write things out in BASIC. And the BASIC would therefore obviously be controlling where the cursor was, like if the next print where it's going to go, okay, put that here, go down a line, it controls the cursor, where it is on the screen, etc., etc. But you can override that by using this command, poke. So what does poke do? Poke takes a number. The first number is the address in memory, so it's any number really between 0 and 64K. And then a comma and another number. So the first byte of memory is 32768. And it doesn't use a sensible like an ASCII type or anything like that. It uses its own representation for memory graphics, and 1 is an A. And as we can see, an A appeared in the top right-hand corner, top left-hand corner of the screen, should I say. And like, so to come down a line, I would then, see I can come back up here, handy thing with this BASIC, I can come back up, so 7, so if I add 40 to this, and 40 to 708 to 768 would be 8. No, it wouldn't be that, would it? It would be 808. And say I add one more to it, 9. That wouldn't work either. 9. It's come diagonally down 1. And if I add another 41 to that, that would be 50. And let's change the character. Let's just use some crazy character from high up. Let's say 100 and, no, that won't work, 178. And there, so we can see it's coming down the screen. So basically you can memory address anything you want onto the screen. So the other things which is interesting is we have CHR string 147. Now there's meant to be a way I can do this using the keyboard, but because I don't have a standard keyboard, it would take a little while to figure it out, so I haven't bothered. But you can clear the screen without typing in CHR string 147. It has a thing called TI, so I can do question mark TI, question mark TI. And we can see here, this is counting the 60th of seconds since I believe the computer was turned on. And obviously it's not that exact, it'll wrap around every 64,000, so it's not the most advanced timer in the world, but it will do for what we want. Once again, the screen memory here, 800 to 83E7 in hex. So what got me into this? So let's try and fill the screen. I think that would be a useful thing to do first. So we write a basic program. So let's just go back to here. Type in new. Okay, so what we want to do is line 10. No, this ain't gonna work, is it? 4. You don't have to use spaces. I equals 32768 2 33767 poke I comma whatever value we want. 89. So let's see what that is. 30 next I. And there is basic filling a screen. We ain't getting 30 frames per second out of that, are we? So in fact, so now if I want to edit this, what you need to do, and was one of the problems with BASIC, that's why you go up in line numbers between 10, 20, 30 if you're an old BASIC head. So if you need to put new lines in, you do 5, so I can add a new line, make it line 5, and say let S equal TI, line 40, let E equal TI, line 50, let T equal, open bracket, E minus S, that's the wrong minus, E minus S divided by 60. Apologies for the, see, I mean, it's just very, very psychologically difficult, you know, typing on a keyboard where the pictures on the keys aren't what comes out. But quit moaning, Paul, get on with it. And then print time taken, I believe it's a semicolon I need here, and then D. So, as it fills the screen, about roughly 5 seconds to fill a screen. Now, I mean, you could probably make that a little quicker, but that is the sort of thing you were talking about. And that was obviously, you know, if you weren't writing a sort of adventure game or typing your name or wanted to do anything more with that, BASIC had its obvious limitations. And when you were typing in and playing these games, they were full of these peeks and pokes and sys's and data statements which were poked into memory. So it was obvious machine code was going on. And then some magazines started, you know, talking about it. And I believe somebody managed to get a 6502 instruction set book. So the first thing, you know, the first thing I ever really wanted to do, you know, because we were always writing little mini silly games, was fill the screen. Just, you know. So let's talk a bit about 6502 assembler. So it's got 8 data bits. So it has a number of registers, it has an accumulator, it has an X and a Y register, they're all 8 bits wide, but it has 64-bit addressing, so it can address 2 bytes, where it can an address that it can get to can be 2 bytes long, so it can address 64K. It's little endian, which is a technical term which basically means when it stores a value, or when it wants to think about a value which is 2 bytes long, it stores in memory the smaller one first. So if you wanted to think about logically the value 1, 2, 3, 4 as a hexadecimal number, so it's 1, 2, 3, 4 hex, that would be stored in memory with the 3, 4 as the first byte and the 1, 2 as the second byte. There is an instruction called sys, which executes machine code. So basically sys, and you give it a number, obviously because sys is typed in BASIC, so it's a number in decimal. It goes to that location and starts running the machine code there. And all PETs, except maybe the very, very early ones, but certainly the ones that we had access to, have what was a machine language monitor built into them. So it's a little kind of mini way of seeing memory, seeing the registers, running that type of thing. There is a much better one called Supermon, which again, I believe we got our hands on or something like that. But that was later on, and I'll have a quick look at it. The other interesting thing here is because of the way memory was tight on a thing called a PET, and memory maps, and it was very hard to discover like what you could do, and it was, you know, for someone who was just trying to get their head around this, it was very hard to understand how the main memory was used, how BASIC globbed it up, what happened to it. There's these pointers which say basically where the start of memory is and the bottom of memory, etc, etc, etc. But there were these two cassette buffers which had, you know, there you can see down there, roughly 200 bytes. What is that? 190 bytes. See down here, the second cassette buffer. So there's basically temporary space when the machine itself is loading things from cassette. So if you're not loading things from cassette, that is not being used. And it gave you 200 bytes where BASIC or no one else was going to go unless you actually started, you know, try to load a program from a cassette. So just a little bit of memory that you could play with and be fairly happy with was yours, and no one else is going to attack it. So the other thing, to get to the machine language monitor, basically anywhere when the operating system as such of the PET encounters an instruction 0, which is break, it will run the machine language monitor. So something normally you could do was, it didn't really matter what the number was, as long as you could find a place in memory that had 0. If you sys to it, it hits a break straight away, and there we go. This is the machine language monitor. So we can use it to display memory. So I can type M 033A space 0350, say. And it displays a little chunk of memory, the start of the cassette buffer I'm talking about here, in byte format. It shows 8 bytes per row. Brilliant. So then we get to what we had to start doing, hand assembly. So with access to books and example programs, you could start to figure out what various instructions meant. So if you wanted to write a little program, which just did the tiniest thing, which recreated poke. So basically we want to write a tiny little program which just sticks a value into the first byte of screen memory. I mean, what would that look like? So we have some of these instructions. Break, again, is the 0 opcode. What that does is when the processor encounters that, it'll jump straight back to the machine language monitor, which is up on the screen there. Then we have things like RTS, return from subroutine. So basically everywhere you got to, when you go into sys, you get there with a JSR, jump to subroutine. So RTS should take you back out to basic, or back to wherever the last place technically you call JSR from. LDA. So there is 3 registers pretty much in this chip: the accumulator, the X, and the Y register. They're all 8 bits wide, and this is how you load it with hash an immediate value. There's the opcode A9. STA, store absolute. And so basically LDA is A9 followed by 1 byte, and that is the byte to load. So like $A9 followed by 50 says is basically load the accumulator with 50. STA, store absolute. That opcode 8D, and then next it's followed by 2 bytes, which is the address you want to store the contents of the accumulator into. And NOP, just no operation, just a kind of useful instruction for padding and leaving some space, because, as we're going to see in a bit, this is notoriously tricky to change programs, because, you know, it isn't a compiler. You can't just sort of insert a line and hope for it. You have to start shifting memory down. So it's all right, pain to do. So if we wanted to write a machine language program to put something in the first byte of screen memory, what would it look like? It would look something like load the accumulator with whatever the value is. So I am going to do at 033A, and this is what I mean by hand assembly. This is how we wrote our first programs. Yes, so well, obviously you do them on a pen and paper first, and hopefully you had a list of opcodes either from a book that maybe we got eventually that had all the 6502 opcodes in it, or maybe from our own handwritten lists of what we could figure them out to be. Yes, life was fun. So we could type in something like load accumulator with, so we'll do 0, 1 again, which is the A character we know. So it would be A9 and load it with 1. 01. Then we need to store that, so that's 8D. And now we need the address that we want to store it in. And remember, we want to store it in 8000, but remember that this is a little endian machine, so the small byte goes first. So there's the 00, and there's the 80. Let's put a NOP because we can, EA. And then let's do an RTS 60, and we don't care about that byte. Hit return. So if I do this again, M033A0350, yes, we have our little program in memory. So hopefully, if this is all correct, that loads the accumulator with 1, and then 8D stores the accumulator, which is the one we have loaded into it, into this address 800. So if I press X to get out of here, I can run it from here, but and then if I do, just knock it up a little bit, and then come up a bit, type in sys 826. And there is the A, as expected. So there is the very, very tiniest hand-assembled machine code program. And like, this was amazing. Oh, this was like amazing. Sad, I know. I've done this page out. I don't want to bore anybody with it, but basically, and I don't think it's that important, but it's the concept of signed integers. I mean, obviously a byte can store a value between 0 and 255, but in a lot of cases we don't want to store 0 to 255. We instead use that same byte to store it as a number between -128 and 127. So what that basically does is it uses the highest bit, the 128 bit, to be the sign bit. And there's a very interesting thing you can do called 2's complement. So 1's complement is you take any binary number, like this one here, and you invert all the bits. And that's 1's complement. And then to get 2's complement, you then add 1 to that with the normal carry rules. So all we've had to do there. And the resulting number, the 2's complement, is minus the original number. And how do we know it is? Well, basically, if you add this to this with carry, you will get 0. So it is a lot, and it's the fundamentals of an awful lot of sort of computer arithmetic and how negative numbers are still handled. Right, so, but again, it's not really for now. That's not amazingly interesting. So the 6502 has a number of flags. Just quickly, it has another flag, which I'll talk to you about quickly in a second, but it has the carry flag. So every time you add two numbers together and there was something left over, it couldn't quite fit everything into the result, it sets the carry flag. And it's also set by shifts. If I subtract with carry, it's set by rotates, and then the clear carry and set carry obviously do it, but it's used as well by add carry, so it adds in the carry flag currently set into the next addition. It uses it in subtract, it uses it in rotates but not shifts, and obviously then there's BCC, branch if carry clear and branch if carry set. So you can make decisions in your program, in your machine code program, based on whether the carry is set or not. Then we have the negative flag. Now it's set by most instructions but not store. So anytime anything does anything, it says, did I do that to a negative number? By negative number it means was the high bit set, and if it was, it sets the negative flag, and if it wasn't, it unsets it. And it's also set by the compare instructions, and it's then used by two BMI branch on minus and BPL branch on plus. And the 0 flag, again, set by most instructions, so it's even loading something into memory or adding something or doing a subtraction. If the result is 0, if what happened as the result of this was 0, then the Z flag is set. It's also set to 1 if a compare instruction is successful, and set to 0 if a compare instruction is not successful. So BEQ is actually checking if Z equals 1. There is another flag called the overflow flag, but take it from me, nobody on this planet knows what the overflow flag does. It's impossible. I've tried to, I tried to understand it once, I couldn't. So just take it from me. Nobody understands what the overflow flag does on a 6502. Well, I presume they do, actually. I'm just an idiot. Right, we don't need it for now. Anyway, let's go on. So it's a quick look at ADC, which we don't really need to do. But basically, there's a complicated thing where you keep a carry coming in and it ripples through your addition and it flows through and gives you a number. That's how 51 and 25 can be equal to 76 if you've got 0. But if you've got a carry already set in the carry bit and you do the same addition, you'll get an answer of 77. So, filling the screen badly.